So I'll start with an introduction about who our team is and what's our mission, and then some examples of how multiphysics simulation was very helpful in our innovation process. And I'll focus on these two projects, the liquid lens and the fluid grating for beam steering. These are just two teaser animations to give you an idea of what it's about, but we'll get into the details shortly. So I'm in the Optics and Display Research Group, ONDR. That is a division of Reality Labs research. And our mission as part of Meta is to advance optical and display technology for the augmented reality and virtual reality products that we have. So the VR products, probably you're more familiar with, they have to be high fidelity, fully immersive, affordable, reliable. And the AR devices need to be all-day wearable, also reliable, high fidelity. They have to be fashionable as well, and also affordable. And these are ambitious long-term objectives. But there's a path forward to it. There's a plan long-term, but also a lot of short-term deliverables and milestones. And if you look, for example, at the Quest 3 headset that was released a few weeks ago, it is much better functionality than the Quest 2 and the one before that. And the plan for the next couple of releases, too, is that they will have big changes and advances. So a lot of these innovations, whether in the display or every other aspect, are coming through to make these devices significantly better than their previous versions. And we also work on fundamental research technologies that will improve AR and VR innovations because we need a lot of inventions to make these goals happen. So like I said, we need a lot of innovations. There are a lot of great teams working from multiple disciplines to make that goal a reality. And that includes physics-based simulation. Many groups at Reality Labs are already using simulation, including us, for the objectives of proof of concept investigations, optimizing products, and root cause failure analysis. But when I joined our group 2 years ago now, a plan was to focus on using simulation more in the innovation process, in addition to the other objectives listed above. So what does that mean? So let me start with a bold statement here that multiphysics simulation is not used enough in innovation. Approximately 3% of patents that could use physics-based simulations use them. And that number is much higher in Reality Labs research, and certainly in our group, it is about 80%. Some mention of simulation in the disclosures and patents. So what does that do? We believe it makes us more creative inventors and innovators, and it helps us do this faster and better. When not just the simulation people, but when the physicists and the chemists and the materials scientists see the simulation results, everyone can come up with better ideas and new ideas when they see what is happening inside the idea that they had in the first place. And we use a lot of engineering and physics fundamentals in our work, so therefore it is not surprising that we use COMSOL. And there's a list of physics here, solids, fluids, heat transfer, species transport, electromagnetics, acoustics and optics, and of course, what's unique to COMSOL, the ability to have your own equations, have all been used in our models. Not in the same model, obviously, but they have all been used even within our small group. So again, not surprising that COMSOL is a very good fit for this type of work that we're doing. So I'll focus on two projects mainly that have been described in patents and publications. And in these two projects, the multiphysics modeling has been very instrumental. These are the fluid gratings, the piezo-actuated lens, and the fluid gratings for pupil steering. So let's start with the first one, the liquid lens for accommodation. So here, we want to do variable accommodation. So what does that mean? It's like, if you look at this surface, it's like a glass you're wearing, it's flat, but also you want to dynamically change to that other curved surface. The deformation, of course, is exaggerated, but you want this to happen dynamically. So that will help focus on different objects, for example, in AR and VR devices. And here is a list of patents that are helping and that are describing some of our innovation there. And behind those, the surface, there's a fluid, and then there's a rigid surface behind that as well. So one of the benefits of this technology is that it will help reduce or mitigate versions accommodation conflict, and that is one of the reasons people get fatigue with long-term use of AR and VR devices, especially when looking at objects that are close, and also extend the use cases to objects that are pretty close. And that has been a challenge for AR and VR devices. The next slide describes this versions accommodation conflict a little better. So imagine looking at the figure on the left, you're looking at an object, let's say 1.5 or 2 meters ahead. Two things happen. Your eyes verge or turn to face that object, and then your lens adjusts to focus on that object. And that has been automated in our brain. We don't think about it. But imagine now, look at the figure on the right, the virtual object is not coming from 1.5 meters away. It is coming from a screen that is close to your eye. So your eye is going to verge on that object 1.5 meters away, but your lens is going to focus on the display, which is much closer. And it happens naturally, but not 100% naturally, so it can cause some fatigue because of that difference between versions and accommodation. So the solution proposed here is to add that varifocal lens between the display and your eye. And that adjusts the focal length so that your lens are focusing on the same distance of, in that example, 1.5 meters away that you would have, your eye is also verging towards. So that is really a good solution, and makes, especially for objects that are pretty close to you. And it's one of many solutions to this problem. So that the liquid lens idea, that is. And even within liquid lens, there are many variations. But I want to focus on this one that is not a standard one. It's a nice invention that we have, where we say, instead of having one surface deformed spherically like many of the glasses we're wearing, let's have the two surfaces, the front and the back, both deform as cylinders, as you see in this figure here, about different axes. Oops. A horizontal and a vertical axis. And you don't see that usually in your glasses, but what is the benefit of that? It's because we start from a flat surface and we want to deform it. Imagine you have a piece of paper and you want to bend it into a cylinder. Easy. You want to bend it into a sphere. Good luck with that. So it is easier deformation pattern. So it's an idea. Is it going to work? Well, we use simulation, and we looked at the mechanical and optical response and found that it's good. It is actually better in some applications, and found some challenges and problems where we were able to resolve some of them through simulation, and then that's how we got it to be that design to go much further than if simulation was not used. So here's a demo of how this specific design works. The animation shows the red surface has the cylinder axis vertical, and the green surface has it horizontal. And even though there are two cylinders, the figure on the right shows the effect, the composite optical power, and it's reasonably uniform, about 11.5 in this figure, which is high optical power, obviously. So how did we simulate that? Well, this one has solid mechanics, of course, and electrostatics, because this one is a piezo-actuated device. And in some cases, we wanted to capture the transient as well. How fast is that going to respond? Like the animation that you see here, of course, the lens is scaled for visualization. It's not that thick in the real world. But so that added fluid flow, and we get results like you see on the left with certain actuation patterns. You get faster actuation with lower distortion. And we were able to improve the design that way. But this is, at the end of the day, an optical device. So we want to look how it behaves optically, because that's really what matters in this case. So we added ray optics. And then this is one analysis where we look at the rays coming out parallel on the left, and as the lens deforms, they will focus to a certain distance, and at a certain point, But if we look at the spot diagram, we find that they don't all go to that point. They go to, in this case, 15 and a half micron RMS distance, which then an optics person can see how good or bad that is, and then but we can compare different designs. And one of the great things about COMSOL is that even though there are dedicated optics software that can do that, having this in COMSOL helps us as inventors and designers to do this whole cycle in COMSOL and see this result live as the lens deform and as we vary design parameters, we see right away what is happening. So that's been very advantageous. So for this kind of project, how did COMSOL help? It helped us reduce the response time. Counter gravity sag. It's not shown here, but gravity can distort this. And if explore ideas like, what if there's astigmatism? What do we do? Simulation helped. And how can we get better, more uniform optical response? And how can we, and also what are the suitable range of properties, mechanical, electrical, or fluidic for the fluid that is behind this lens, to make us achieve these objectives and of good optical quality, fast response time, reliable solutions, and so on. So on to the second example. This is another form of active optics. In this case, an optical component that changes its properties with a signal, which in this case also is a voltage, just like the previous example, except that in this case, the voltage is changing the direction of a light beam. And there are numerous applications for that, including pupil steering. So a little intro on what pupil steering is. Here's a simple display on the left that sends a signal to a passive combiner that gets it back to your eye, and you see from the angle going to the eye that you have a wide field of view. Good. But if for that design you look to the right, as this right figure shows, then the image is not going to be good anymore because it is not focused, it's not coming directly to where your eye has moved. And in practice, there are more complex displays with waveguides, pupil replication, and so on, but this is just to illustrate the concept, which you will see in the next slide here, of now an active combiner. Look now on the figure on the right, the signal has reached your eye. So if I flip back and forth between the two, you see that what's changed is the angle at which the optical rays are coming towards your eye because of that active pupil steering technology. So how does it work, this fluid grading? Well, there are two fluids in the light and dark gray that you see on the left. And the interface between them is straight in the beginning. There's nothing causing them to be anything different. But then there will be an electric field, and you see some voltages and grounds applied on the left. Basically, the electric field with the dielectric mismatch between the two fluids will have a force that will distort that interface. And there's surface tension that will want to maintain that interface. And density matters as well, of course, and viscosity. But when it deforms to the figure on the right, then you have a diffraction grading. Some of the light coming will go through directly, but others will be diffracted to the angles that you see in that figure. And here are two simulations we did for this. One of the good advantages of using COMSOL is that we have multiple formulations for these multi-phase flows. And the solution on top, it's a stable wave. So we use the much faster, easier to converge moving mesh method. In the applications on the bottom, we have actual full columns developing. It's unstable, meaning you cannot get a certain height. But we use phase field in this. And in 2D, they're both fast, but in 3D, there's a big difference between these two. So the ability to select the right formulation based on the problem, even within that specific application, was very useful. And so there was this idea, and then we did the simulations, and then people did testing to see, this is a relatively new idea. Is it going to work? And it's going to give us the amplitude that we expect. I mean, the physics says it's going to work, but is it going to practically be useful? So we did experimental validation. And I shouldn't have said we, because I'm not involved in that, but the team did experimental validation. And in this case, with one fluid, with the electrode pattern that is 20 micron spaced, and grading amplitude of 700 nanometer developed, as the figures on the right show. And we simulated that one fluid case in COMSOL, and we got results that were right on, the same amount of amplitude as the experiment showed. And of course, everyone, good story there, everyone's happy, but all of you as simulation people would appreciate the enthusiasm we have when we get this kind of great agreement first time with a model. But it doesn't always happen like that, and especially in research. It's actually not even the norm to expect this kind of agreement right away. So some cases, it could be because the model is wrong, but I would never admit that. But in many cases, it's really because there's so much complexity that something is wrong, and we start a failure or root cause failure analysis, and that can be done without simulation. People can do this by looking at different factors and doing failure analysis. But even then, simulation is useful, because let's say you look at the example from the accommodation previous example, you can find, hey, the deformation is not as much or is not as uniform. So people can say, well, maybe this electrode is not working, or this material property is different, or this factor. And then we can say, yeah, let's test that hypothesis with the modeling. And together with testing and modeling, we usually find the root cause of failure much faster. So going back to this example again of the pupil steering, this is again an optical product. So having the deformation was good, and the flow pattern was all good, but we want to see how useful is it as a grading. So one path would be to go again to the dedicated optics software and check that, and we do that. But again, having this in COMSOL, as the deformation of the fluid happens, we want to live find the efficiency of the grading, has been very useful. And in this case, unlike the previous example where it was ray optics, this one is wave optics. And COMSOL has the capability to calculate the diffraction grading, usually for a fixed structure, but now we apply it to a deforming structure. And we find graphs like you see here, where the grading amplitude 0, you have only transmission mode order 0, which is direct transmission happening, 100%, or close to 100, depending on some reflection. But as you have the grading amplitude, you start getting mode 1 and mode 2, and it also varies with incident angle and so on. So having all that calculated live as you have your simulation and as you run your optimizations has been very, very useful. So the simulation then helped us with the proof of concept, optimize and improve the fluid grading, and answer some questions and address some challenges, including those listed here. How can we get larger amplitudes, because that's helpful? How can we change the pitch? How can we get blazing, which is those sinusoids curving to one side rather than being symmetric? That's also advantageous, and reducing the response time. But there's one of the researchers then came up with this great idea. We have a problem with gravity, so why not replace one of the fluids with a soft gel? That researcher wasn't me, by the way, but I said, yeah, I can analyze that. Replace the fluid by gel, see what happens, because that has many advantages to when it comes to dealing with gravity. So no problem. Now, instead of a multi-phase flow, it's a FSI problem with a fluid and a solid. But then we hit a snag. The surface tension is very important here, right? But there's no surface tension at the fluid structure interface in COMSOL or in any other code, as far as I know. But because it's not that common, really, but we need it here. The surface tension is still important for that soft gel, so not a problem. We implement it in COMSOL as a weak form, and that is unique, of course, to COMSOL. And we test it and validate it. It works, great. So then we go back to our main problem again. Is the gel going to work? And it turns out that, yes, there is a range of properties for which the gel still achieves that grading that you saw. and helps with people steering, but it's not too detrimental to the results, and it does not reduce the amplitudes too much. So that is a success. And these are the two main examples that I'll talk about, but also I want to mention two other examples, one slide about each, to give you an idea of more applications where we use multiphysics simulation and COMSOL specifically. This is, first one is ultrasonic gaze estimation. Gaze estimation refers to estimating where your eye is gazing, because a lot of things follow from that and for AR and VR device. And it's an established technology. This is not new. But most of the techniques used for gaze estimation are based on light or optics. And it makes sense. But there are techniques based on ultrasonics. So are they going to work? And are they going to work for us? Are they going to be better for some AR and VR devices to have an ultrasonic-based method? This is a paper published by the team who did that research at Meta, and I was back at Verist, and Verist was working on this project with them to do the simulations that show for a certain transmitter, like the one you see here, and receiver combination and other variations or permutations, when and in what conditions is an ultrasonic gaze detection better, and so we would move the eye and the gaze and the model here to different orientations and do different variations of faces and eyes and so on. And we're able to assess that technology to see when, if any, can it be a good replacement for the more common light-based gaze estimations. And the last example is thermal innovation for both AR and VR. Thermal is a problem. These are devices that we wear close to our, on our face, literally, and they pack a lot of power. People want high resolution. People want high light intensity. So getting rid of the heat is a problem. And it's a limiting factor in many of the designs. So we have to look at novel solutions. We cannot take what is out there now and not look forward to better heat transfer solutions. So the figure down on the left is a material that does for the cover of a VR device that does not spread the heat too well, so you see the heat source is localized and in the middle doesn't spread as efficiently. The figure on the right is an experimental case of a different material that is a better conductor, and no surprise from the IR image here that the temperature is more uniform. And we can look at other solutions that are, some are common, well-known, like heat pipes, phase change material, highly conductive polymers. But the beauty of simulation is that we can look at more extreme solutions or innovative solutions. Like there were some papers recently came out on thermomagnetic convective-based cooling. We're not going to develop a test facility for every idea that comes out like that, but we said, yeah, we can test that computationally, virtually, and by replicating what's in that paper, making sure we got it right, and then testing how it would work for our VR and AR devices. And regardless of whether this idea works or not, having that approach to try different things leads to some ideas making it into reality. And like I mentioned earlier, we need a lot of innovation to have these devices meet their long-term targets that I discussed earlier. So in summary, we use multiphysics modeling a lot in AR and VR innovation and in improving our products for both AR and VR devices. And we use COMSOL a lot in proof of concept, improving, optimizing designs, but also in the innovation process itself. And what's next? Well, we want to keep doing this for more applications. The more and more people are using simulation because they see the benefit, just as the previous speakers today and yesterday mentioned. And another objective that we're looking forward to is to better leverage AI and machine learning in the research and innovation process. Meta is known for these and applies them successfully in many other areas, but we want to apply them in physics-based applications and specifically in research. And last thing is I want to acknowledge my co-authors, the rest of the simulation team, the rest of the team. It's been very interesting and fun working on these projects. I want to acknowledge our the consultants we work with, including Verist, and finally ComSolve for the great product that they have and support of ComSolve, for putting up with my questions every now and then, and for keeping the product in great shape. And thank you for listening.